A Canadian football field is 110 yards long. Let's say that we have 110 students at Holy Trinity, and we line one student up at each yard of the football field. So we've got 110 students evenly spaced 1 yard apart, and so on. It's pitch black outside. It's midnight. It's pitch black. And we blindfold everybody. So there's no way that these 110 people can see where they're going. But I'm out there and I'm directing them. I want to direct each one of those people to go directly across the football field, like this. 110 people directly across the football field. And I tell them randomly, it's your turn to go. And then it's your turn to go. And then it's your turn to go. And what I notice when I send all 110 people across this football field is that the vast majority of these people, the vast majority, almost all 110, let's say 100 of these people end up going straight across the football field, unchanged. Okay, they just go right straight across, and on the other side to where they end up on the same yard line as they started. Okay, the vast majority go straight across. But not everyone. I send 110 people across one at a time. 100 of them go straight across. But 8 of them don't go straight across. 8 of them change paths. They still make it to the other side, but they change paths. So let's say this guy goes over here, and then all of a sudden he ends up over here. And then this guy he ends up over here. So some of them, a few of them, are deflected. They make it across to the other side, but their paths are deflected. Let's say it's 8 of them. We got 2 people left. What happens to the other 2 people? A few of them, not very many, and in this case it would only be 2 of them, bounce back. So we go up like this, and then it comes back, straight back or back at an angle. So what do we, if we can't see what's going on here because it's pitch black and all these people are blindfolded, what do we conclude from this? Well, firstly, we would probably conclude that most of the football field is clear, right? If 100 people were able to go straight across, then there must have been a mostly clear football field with nothing in the way. Does that make sense? 8 people were deflected. They made it to the other side, but 8 people were repelled by something right here. Something right here repelled them. Now, what repelled them? Maybe a smelly football player. Okay, maybe there's a smelly football player in the middle, and as they're running across like this, then they change paths, right? It's got to be small. Most of the football field is empty space. So if there's something there to cause a deflection, it's got to be pretty small. 100 people made it straight across. Only 8 changed direction. So whatever it is that's causing them to change direction, that smelly football player that's repelling them, whatever the case may be, it's got to be pretty small. Now, 2 of them end up bouncing back. What does that tell us? Well, they must run into that smelly football player. But we know something more about that smelly football player besides the fact that he's smelly. He's got to be heavy, because if you run into a light football player, let's say it happens to be a 2-year-old standing in the middle of the field, and you're blindfolded, and you run into him, what happens? You run right through him, right? But that doesn't happen here. We're not running right through them. We're bouncing off of them. So whatever it is that's there must be heavy. So what's our model of this football field? We've got a football field, a big football field that's mostly empty space. But we do have this small, heavy, smelly football player in the middle of the football field. Ernest Rutherford and his assistants Geiger and Marsden performed an experiment that's similar to this using alpha particles and gold foil. They had this box. This box that contained a radioactive material that generated alpha particles. It wasn't a box of alpha particles. It was a box of, like, I don't know, uranium or something that generated alpha particles. It decayed into alpha particles. Now, these alpha particles would leave this box. They get fired this way at this thin layer of gold foil. When I talk about a thin layer of gold foil, I mean something like aluminum foil, except thinner and made out of gold. Really, really thin layer of foil that's made out of gold. That's important because gold is heavy. Surrounding this, we have this screen that we call a scintillation screen. And this screen is designed to glow when alpha particles hit it. Alpha particle strikes it, it glows, therefore we know where the alpha particle hit. Rutherford and his assistants noticed that most of the alpha particles went straight through, just like most of the football players went straight through. What did he conclude from that? What did we conclude from the football analogy? Most of the football players went straight through because most of the football field was empty, was clear. So most of the atom is, Jesse, empty space, yeah. Not all of them went straight through, though. Some of them were deflected. So some of these alpha particles went down like this, or went up like this. They still went through, but they didn't go straight through. Just like some of our football players, some of our people running across the football field were deflected. What deflected the people running across the football field? It was something that's small and repelled them. What repelled them in the football field? It was a smelly football player. What would repel a positive alpha particle? Something that's positive. What would repel a positive alpha? Something that's positive. So the conclusion that we drew from this, or that Rutherford drew from this, was that there is a small positive, we'll call it a nucleus, a small positive nucleus. A few of the particles bounce back. What did that tell them? Well, two of the people that ran across the football field bounced back as well. 8 of them were repelled by the smelly football player. 2 of them bounced back. What do we know about the smelly football player? Besides the fact that he was smelly, he must have been heavy. He must have been pretty heavy. So this nucleus, not only is it small, because most of the atom is empty space, not only is it positive to repel the alpha particles and deflect them off their path, but the nucleus has got to be heavy as well. If the nucleus wasn't heavy, there's no way these alpha particles would have bounced back. They would have went straight through, like you would go straight through if you ran across the football field and ran into a little kid. So we go from a model of an atom that looks like this, which was the Thomson plum pudding model, the Thomson chocolate chip cookie dough model, the Thomson raisin bun model of the atom. We go from that to this. We have a small, dense, positive nucleus. And the electrons have got to be somewhere because Thomson discovered the electrons, and that was real. But they're not just floating around in the sea of positive charge. They're orbiting around this small, dense, positive nucleus. Some people would say this is an evolution of the atomic model. I'd almost say that this is a revolution, in this case, of the atomic model. The next one that we're going to talk about is more evolutionary. To me, this is revolutionary because we're going from something so simple as having, look, there's just positive charge and negatives floating around, to saying look, yeah, there's positive and negative, but this is really what it looks like. In the middle, empty space, electrons orbiting around it, right? Yeah. Okay, that's not what I was meaning by that, but sure. By the way, the Rutherford model of the atom is often known as the planetary model because it reminds us, or it should remind us, of the planets orbiting around the sun. If the Rutherford model was revolutionary, some people would argue that the Bohr model is revolutionary as well. I would say that it's more evolutionary because it relied on the basic structure of the Rutherford planetary model of the atom, but there was some important differences. Let's say that I'm Niels Bohr. I come along and I read about Rutherford's model of the atom, the planetary model of the atom. Rutherford says that the atom consists mostly of empty space. I'd agree with that. If I'm Niels Bohr, I agree with that. The atom consists mostly of empty space. Rutherford says that there's a small, dense, heavy, positive nucleus that's inside this mostly empty space. If I'm Niels Bohr, I'd agree with that too. Electrons orbit around the nucleus. Yeah, I agree with that. So what separates Niels Bohr, his model, from the Rutherford model of the atom, the planetary model of the atom? Niels Bohr talked about electrons not just orbiting around the atom wherever they wanted, but rather they orbited around the nucleus on specific levels. They had to be in a specific spot. And each level is characterized by a specific energy. Most of you guys have probably been to a hockey game, a Flames game at some point in your life, if you're a hockey fan, that is. You know, you notice when you go to a hockey game, there's three levels of the Saddle Dome. There's three seating levels. So level one, level two, level three. And usually, just like in the atom, you usually want to fill up the lower level first. If there's empty seats down on the first level, they usually get filled up, right? People go down and fill them up if they're not full already. But you also notice that not only do people fill in the lower levels, not only do people have to be on a specific level to watch the hockey game, level one, level two, or level three, but each level is also characterized by a specific amount of energy. Okay, the first level tends to be people that have some more money because the tickets cost more. The first level is often filled by people with maybe dressy clothes, like suits, people coming from work with company tickets or whatever. It tends to be less energetic. People don't get up and high five and celebrate as much when a goal is scored. Sometimes they do, but generally, the first level is characterized by less energy than the second level. People in the second level are kind of those middle income people. That's where I would go to sit in the second level. And people get excited when a goal is scored. And it seems to be more energetic than the first level, right? The first level is characterized by some energy. The second level is characterized by a different amount of energy. But if you go up to the third level, the sport check zone, or the press level, they call it now, that's where people don't spend quite as much money on a ticket. They tend to spend more money on alcohol. And that's where people are really energetic, is up there on the third level. You got three levels, and people have got to be on one level or another, and each level is characterized by a specific amount of energy. So we have the electrons existing on levels. This is one big thing that differentiates the Bohr model of the atom from the Rutherford planetary model of the atom. Next thing, we call it stationary states. I'll explain that. Electrons orbit around the nucleus in circles on specific levels. Each level is characterized by a specific amount of energy. Let's pretend my keys right now on the end of this string are the electrons orbiting around the nucleus. Maxwell said, think back to the last unit. I know you guys, some of you guys don't want to think back to the last unit. You want to forget that one forever. We do have a diploma exam in 3 weeks, so you probably want to remember it at some point. Electrons orbiting around the nucleus, they're accelerating. There's a centripetal acceleration there. And Maxwell said that accelerating charges generate EMR. So according to Maxwell's theory, these electrons that are orbiting around the nucleus should produce EMR. But if they give off EMR, then they're going to have less energy than they had before, right? And watch what happens if they lose energy. These electrons spiral right into the nucleus. If they give off EMR, then they spiral right into the nucleus, and that doesn't happen. So for whatever reason, they don't follow Maxwell's law of electromagnetism that said EMR is generated by accelerating charges. It's as if the electrons aren't accelerating. In fact, it's as if they're not even moving. It's as if they're stationary. It's as if they're in a stationary state. So we're going to say orbiting electrons experience a centripetal acceleration. Write that out if you don't know what this, if you're going to forget what that symbol means. They experience a centripetal acceleration. They should emit EMR, but they don't. So it's as if they're stationary, not accelerating toward the center of the circle, experiencing the centripetal acceleration. Finally, the last thing that separates the Bohr model of the atom from the planetary model of the atom, the Rutherford model of the atom, is the idea that electrons on these levels can make transitions. If you've ever sat in the third deck of the Saddledome, you know that to go in there, you have to go in on the concourse level. And then you have to climb a whole bunch of stairs, and then you have to climb even more stairs. There's a lot of stairs to climb. You can make a transition to the third level of the Saddledome, but if you do, you need to make sure that you have some energy. You need to make sure that you absorbed energy at some point. You need to make sure you've ate your Wheaties for breakfast, or had a Starbucks coffee or a Red Bull before you went up those stairs, because you need to absorb energy to jump to a higher level, to go to a higher level. Electrons can jump to a higher level as well. And they jump to a higher level by absorbing energy. And usually that energy that they absorb is in the form of EMR. Not always. They could absorb kinetic energy from stray electrons. They could absorb electrical energy. They could absorb any one of a number of types of energy, but usually they absorb a photon. You shine light, you shine EMR on atoms, and some of that EMR is taken by the atoms to cause the electrons to jump to higher levels. Okay. Ethan goes up to the third deck of the Saddledome, gets his energy by having a coffee. Hey, Jesse goes up to the third deck by drinking a Red Bull. But most people, they go up to the third deck, get their energy by just having breakfast, having lunch, having dinner, and receiving their energy in the normal way. Okay, most electrons jump by absorbing EMR, but some of them absorb energy from some other form. Now, electrons can also fall. To a lower level. If you're up in the third deck of the Saddledome, it's two of you, let's say, and you see a half a dozen empty seats through the whole first period, nobody sat in them, in the first level, what do? Maybe you go down and sit in those seats. You make a transition to a lower level. But as you do that, maybe there's this little shriek of delight, of glee as you're running down the stairs because, hey, I won. I won. I get to go down to the first level. I only paid for third level seats. Okay? When electrons fall to a lower level, they give off energy or they emit energy. And that's not usually in the form of EMR. That is EMR. Remember back in our EMR unit, we talked about the different ways in which EMR was produced. Radio waves and microwaves were oscillating electric charge. X-rays were rapidly decelerating electrons. Gamma rays were nuclear decay, which we've talked about. Infrared, visible light, and ultraviolet were produced by, remember this? Transitions of electrons in atoms. It's exactly what we're talking about right now. When electrons go from a high level to a low level in an atom, they give off EMR. Visible light, ultraviolet, infrared, occasionally an X-ray.